One other method for synthesizing ethers is the so-called alkoxymercuration. Alkoxymercuration, that should be reminiscent of the oxymercuration, right? You remember that? Oxymercuration. The only difference between the oxymercuration and the alkoxymercuration is just two little things. Number one, instead of being mercuric acetate and water, what you use, right? And so instead of being mercuric acetate, here we utilize the trifluoro version of that. So it's also a mercury salt, but it is the trifluoro version, OCO CF3 instead of CH3. And then the other minor difference is that instead of being water, as you recall, we were using water and we were having a hydration of an alkene. So here, instead of using water, we use an alcohol. In this particular example was methanol, but in general, you can use any alcohol. And so that will be the recipe. Step number one, you will react your alkene with the trifluoroacetate of the trifluoroacetate. And then after you form the so-called mercurinium ion, then instead of using water as the nucleophile, here we use an alcohol. So in this particular example, let's try to rationalize what we have here. So here you have your carbon-carbon double bond, right? And so and then because you are reacting this with mercury, so the double bond will be gone, and you will form a mercurinium ion. Mercury, positively charged, still with one of the acetate units. And then instead of having a water molecule attacking one of the carbon atoms of the three-member ring, you will have an alcohol. How about the regiochemistry of this reaction? So the regiochemistry, we said that the observed regiochemistry is Markovnikov. What does it mean, Markovnikov, in this case? It means that the alcohol will end up being attached to the carbon atom that is more highly substituted. So in this particular case, the more highly substituted carbon is the one that is attached to the benzene ring. So and that's why in the final product, you will have the methanol that get attached on that particular carbon atom will end up giving you an ether in which the methanol unit got added on the carbon atom that was more highly substituted. So this method is particularly useful when you want to synthesize a compound that you cannot synthesize using the Williamson ether synthesis. For instance, this one here that I am circling in yellow here, so that compound will be problematic to synthesize using the Williamson ether synthesis. Why? Because the two halves of the ether, both of them are highly substituted, right? So here the rule of using the more highly substituted alkoxide and the less highly substituted alkyl halide, it doesn't work because both halves are highly substituted. Both halves are tertiary. So I couldn't be able to do that, and I will be at very, very high risk of getting an elimination reaction taking place. So what we can do is that we can use an alcohol like this one here. So here we have a tertiary alcohol, and I can react this with mercury trifluoroacetate. So I'm going to write it like this. Let me just write it down explicitly. OCO CF3, and then OCO CF3. So what is going to happen is that you will have attack of the double bond on the mercury, attack of the mercury on the other carbon of the double bond, and departure of one of the trifluoroacetate units. At that point, you could have made the three-member ring, right? With still one of the trifluoroacetate units attached. And the mercury is positively charged. And then now it comes the question of the regiochemistry. Which carbon atom is more highly substituted, top or bottom? So this is the top, and this is the bottom, right? So which one is more highly substituted? The bottom one. So because the bottom is the more highly substituted, the result will be that the attack of the alcohol will take place there, right? So here now I have my alcohol that will attack all the way on that carbon atom. And then when the system opens up, right, when the system opens up, then I will end up with the left-hand side of the final product. That one was derived from the alcohol, right? Even the oxygen was derived from the alcohol, right? And then the right-hand side of the molecule was derived from the alkene, right? So this portion here was derived from the alkene. There you have the initial alkene. And so there you go. The reaction proceeds with Markovnikov regiochemistry. The next reaction we have in this chapter is the so-called the acid catalyzed cleavage of the acid catalyzed cleavage of ethers. And in some way, this reaction is a little the opposite of the method of the Williamson ether synthesis, meaning that when you have an ether, let's say you have ethyl phenyl ether, so the first thing that will happen in this reaction when you degrade this, when you cleave this using a HBr or HCl, the first thing that will happen is that you will have protonation of the oxygen of the ether. Protonation, and then you will have a nucleophilic attack of the bromine on the carbon atom that is more accessible. Which one of the two carbon atoms is more accessible in the case of the ethyl phenyl ether? Well, so once you form the intermediate, so then that means that you will have protonation of this oxygen. It will be protonated. So then now attack on this carbon atom or attack on that carbon atom. So the first one, position A, actually that is a nonsense, right? Because if you are going to have a backside attack, that means that the nucleophile, the Br minus, will need to get on the inside of the benzene ring. That is impossible. But attack on the other carbon atom, that is okay. Position B is fine because that is a primary position, right? So that's why that will be the logic thing, that bromide will attack on the primary position, and then the benzene ring will go away with the OH, and it will end up forming phenol. Here we have another example, ethyl isopropyl ether. We have one half that is a secondary position, while the other half is a primary position. So whenever you have competition between a primary and a secondary, the primary will take precedence, it will be the preferred position, and that's why we have the attack of the I minus took place on the primary position. And so that is the general rule in this case. Okay, and then the next reaction we have is the so-called Claisen rearrangement. The Claisen rearrangement is a very cool reaction. I really like this reaction. So what happens here? First, we need to learn how to make an allyl phenyl ether. Allyl phenyl ether. So here is the product, allyl phenyl ether. So we can use the Williamson ether synthesis. So we can deprotonate phenol with sodium hydride. We are using exactly the same procedure of the Williamson ether synthesis. Deprotonation, we form the alkoxide with 3 lone pairs of electrons there, negatively charged. And then you have nucleophilic attack of this on the carbon atom of the allyl bromide. Displacement of the bromine, and in that way you have formation of the allyl phenyl ether. And then here it comes the actual rearrangement step. So our starting material looks like this. Looks like that. So here we have a very typical concerted reaction. All the bond making and the bond breaking takes place simultaneously. This pair of electrons goes to form a bond to the carbon. This other pair of electrons goes to form a double bond there. And then finally, this pair of electrons goes to form a pi bond between the oxygen and the carbon. So what do you get out of that? If I follow the instructions of the arrows, I can see that I will end up with a ketone here. And then now the attachment is through that carbon atom, and I will have a double bond hanging there, right? Now, never forget that there was a hydrogen atom there, right? That hydrogen atom is still there. So then at this point, what will happen is that you will go through a tautomerization reaction. That you can envision that as having a base that will abstract a proton, will rearrange the electrons like that, and then that base also will give you back the proton in a different position, right? So what do you get when you do that? You get that final product, which is a phenol. So I will stop here, and then I will give you another example in the next video.